So this is the stoichiometry tutorial, and so before we get started, I want you to have out a calculator and paper and pen to write this down because I really feel like it would help you to work the problems along with me instead of just watching me work them out. So if you don't have that stuff, please pause the video and get those things together, and let's get ready to get started. All right, so first step in all stoichiometry problems is we have to start with the balanced equation. So we have to start with the balanced equation. Without that, we cannot work these problems and get them correct. And then we're going to need some conversion factors, and we've got several conversion factors that we could use. If we're dealing with volume of a gas, we're going to always use this 22.4 liters per mole. If we're dealing with mass, we're going to be using the molar mass right here, which is the grams of a substance for 1 mole. And then if we're dealing with atoms or molecules, we're going to use Avogadro's number, which is the 6.02 times 10 to the 23rd. Every problem we do is going to require a mole ratio. And remember, we get that mole ratio from the balanced equation. That's why we have to start with the balanced equation. Kind of the general formula that the mole ratio is always going to be is you will always have the moles of given from the problem on the bottom because you're trying to get rid of that, and you'll have the moles of unknown on the top because that's what we're trying to get to. And that is going to be for every single problem, whether it's a mole to mole, a mass to mole, even from the grams to liters. All problems are going to require that mole ratio. The mole ratio is our conversion factor of how we get from any of the compounds to any of the other compounds. And it does not matter if we're trying to go from one reactant to another reactant, or if we're trying to go from a product to reactant or product to a product. We can relate anything in the balanced equation to anything else by using this mole ratio. All right, so let's get ready to work some problems. All right, let's get started with the first problem. So of course the first step is always to balance the equation, and so we're going to do that real quickly. If you are still struggling with balancing equation, that needs to be a different tutorial. That you need to come in and we'll sit down one-on-one and see where you're still struggling. So let's balance this very quickly. I noticed that right here I've got 2 aluminum, so I'm going to put a 2 right here. I then noticed that I have 3 sulfates, so I'm going to put a 3 right here to take care of those sulfates. Remember to treat your polyatomics as 1 unit on both sides. And then when I do that, I see that now I have 6 potassium, so I'm going to put a 6 right here. And then by doing that, it also took care of the 6 bromine on the other side. So now that we're balanced, we can go through and look at our problem. So biggest hurdle sometimes is actually starting the problem or discerning from the problem what it's asking us for. So let's spend a few minutes trying to look at that and see what we need to do. So I noticed, well, let's read the problem. How many moles of potassium sulfate is required to react with 3.5 moles of aluminum bromide? So I am given the 3.5 moles of aluminum bromide. So something that might help you as you're going through these problems is let's go list it right underneath the balanced equation so we know what we're dealing with. We've been given 3.5 moles of aluminum bromide. Okay, and what is it asking for? It says how many moles of potassium sulfate. So let's go find potassium sulfate, and that's right here. So we're going to say this question mark moles. So this is what we want to solve for. Okay, so let's start with the 3.5 moles. Okay, do our grid. This is going to be a mole to mole, right? Because we started with moles and we want moles. So it's going to be mole to mole. So we're going to write that down. And then remember, whatever unit I have right here, I immediately want to put it down on the bottom in the next step. So I'm going to put moles of aluminum bromide. I'm going to go to my balanced equation and I'm going to see that I have 3.5. Just kidding. I have 2. Sorry about that. I have 2, so I'm going to put a 2 right there. And I'm trying to go to the potassium sulfate because that's what the problem said right there. So I'm going to put moles of potassium sulfate on the top. And then I see that I have a 3 there, so I'm going to put a 3 there. So now I have my mole ratio. What this is saying is that for every 2 moles of aluminum bromide, here I need 3 moles of potassium sulfate to completely react. And so now we're ready to do our calculations. So I'm going to say multiply everything on the top and divide by the bottom. So the way that I would do this is I would say 3.50 times 3 equals, and then I would divide it by 2. And when I do that, I get my answer of 5.25, because I need 3 significant figures, moles of potassium sulfate. All right, so let's hopefully everybody's following along, and let's work another problem. All right, first things first, let's balance this equation, and I'm going to give you a little hint. It is a little bit difficult to balance. It takes a little playing around with it, but I want you to pause the video, try to balance it, and then come back and see if you balanced it correctly. How'd you do? All right, let's read the problem now. So we have, in this reaction given below, what volume of oxygen is going to be used when 85 liters of ammonia reacts. And then, of course, it says assume STP. And so we're going to be using that 22.4 liters per mole. We're going to need to use that as our conversions today because we're dealing with volume. So let's go underline what they gave us in the problem, which was 85 liters of ammonia. So let's put the 85 liters here because that's what we've been given. And what is it asking for? It's asking for what volume of oxygen. So we're going to be looking for volume of oxygen, and it wants it in liters. So this is a liter to liter problem, okay? So let's get started with what we know, 85 liters of oxygen, of NH3, so put that there. I want to do 22.4 liters of NH3 per mole because that's the way I convert liters to moles. Remember, everything has to be converted to moles so that we can use that all-important mole ratio. Okay, so we've gotten rid of liters. And so now we need to do is get rid of moles. So I have moles of NH3 here. So I'm going to immediately put it on the bottom there so that I can get rid of it. So I have moles of NH3. I go look at the balanced equation and I see that I have 4. So I'm going to write a 4 here. And then I'm trying to get to oxygen. That's what it's asking me for. So my unknown here is oxygen. And so I go look and I see that I have 5 moles of oxygen here. So I'm going to do 5 moles of oxygen on the top. So now I've gotten rid of moles of NH3. And we're in moles of oxygen, and it's asking for volume, which is right here. And so remember, we've got to do liters. So we're going to use this conversion factor again on the other side. So for every 1 mole of oxygen, I have 22.4 liters of oxygen. Remember, this conversion factor for volume of gas is for any gas. It doesn't matter what kind of gas we have. So now we need to do the math. So I have 85. So I get to this and I say 85, and I've got a 1, so I can ignore that. So 85, and then I have a 22.4 on the bottom. So 85 divided by 22.4 equals, get to the next step, and I say times 5 equals, divided by 4 equals, and then times 22.4 on the last step. And when I do that, I should get, I get 106 liters. And that's my answer because I need 3 significant figures from right here. And so that is my answer, liters of oxygen. All right, next problem. So obviously, first thing we need to do is balance this equation. And so we're going to balance that very quickly. I see that I have 2 sodium on the product side, and I only have 2 sodium on the reactant side, so I'm going to put a 2 right there. And then I notice that I have 2 hydrogen for this H2SO4, and I only have 1 hydrogen on the other side with HCl, so I'm going to put a 2 there. And then, of course, that also ends up balancing my chlorine. So now I'm ready to start reading the problem. It says, if excess sulfuric acid reacts with 30 grams of sodium chloride, how many grams of sodium sulfate are produced? Okay, so remember I mentioned in class when you see this excess sulfuric acid, that means we can kind of ignore it. Okay, it's not going to show up in this problem. The reason we oftentimes have to have these extra words in there is because we have to know how to write the equation of what's reacting. So let's continue on. It says if excess sulfuric acid reacts with 30 grams of sodium chloride. So that is my given, right? That's what they're giving me in the problem. So let's go write it down under here, 30 grams And then it says how many grams of sodium sulfate are produced. So we're going to be looking for grams of sodium sulfate. So since I'm starting with grams and ending in grams, this is a mass to mass problem. So that means we're going to do all 4 steps. All right, so let's start with the 30 grams. Oh, that's really messy. So 30 grams of sodium chloride, and then we're going to do our grid. When we start in grams, that means we're going to need a molar mass. We've got to get rid of the sodium chloride. So we're going to do grams of sodium chloride to 1 mole. That's the only way we can convert our our grams to moles. Okay, so we need to add up. Sodium is 22.99 plus chlorine is 35.45. So when we add those together, we get a molar mass of 58.44. Okay, so then that cancels out our grams. Now that we're in moles, we can go get our mole ratio from the balanced equation. So we need sodium chloride on the bottom. We have 2. So we write 2 moles of sodium chloride on the bottom. And then, of course, we're going to this sodium sulfate. It's what it asks us for. We forgot to put that gram right there. Okay? So then we see that we have 1 mole of sodium sulfate. So we cross out our sodium chloride. And we're going to need a molar mass because we're trying to go moles to grams. And the only way to go from moles to grams is use a molar mass. So we're going to put 1 mole of sodium sulfate. And then we're going to get the molar mass of sodium sulfate to go on the top. So we need 22.99 for sodium times 2 plus sulfur is 32.07 plus 4 times 16 for oxygen. And when we add all that up, we get a molar mass of 142.05. So now we're ready to do our calculations. So you can do this one of 2 ways. You can multiply everything at the top and then divide by everything on the bottom. You just got to be careful with your order of operation. The way I like to do it is I start with this 30 grams. I go to the next step. I have a number on the bottom, so I say divided by 58.44. Then I go hit equal. Then I go to the next step and I say I've got a number on the bottom, so divided by 2 equals. Then I go to the next step and I have a number on the top and I multiply it by 142.05. And then when I hit equal, I should get an answer of 36.5 grams of sodium sulfate. Okay, if you had trouble with that, then you should pause this video before you go to the next one and recalculate that and see if you can't get that. Okay, so for the last 3 problems we have in this tutorial video, we're going to try pausing it and then you working it out and then you checking to see if you got the answers right. Because watching me set it up every single time, it seems easier, of course, when I'm doing it, but you need to get good practice of setting it up yourself, and then you have a way to check yourself, okay? So let's get started. Luckily, we already have a balanced equation. So it says how many liters of hydrogen gas are produced if 15.9 grams of hydrochloric acid react with excess zinc metal. So when we see excess zinc metal, we can know we're not going to be using that. When we see this word, how many liters, we know that we're going to have to use that 22.4 liters per mole. So we're going to have to use that conversion factor somewhere. And then our given is 15.9 grams of hydrochloric acid. So let's go jot it down underneath the already balanced equation. So we're going to have 15.9 grams, and we are looking for liters of hydrogen. So let's get started. I've showed you what I want you to start with. I want you to pause the video and I want you to try to set this problem up yourself, and then let's see if you can get it. All right, so hit pause. All right, how did you do? Hopefully you got that right answer. If you didn't, again, pause the video and walk through the steps of what I did and see and compare them to what you did and see where you're having the disconnect. So let's move on and try another one once you've finished with this one. So here's the next one, and let's start by balancing the equation. I've got 2 oxygen on one side, 3 on the other. Anytime I see a 2 and a 3, that means I'm going to need a total of 6. So let's make both sides be 6 by putting a 3 here and a 2 here. And of course, when I put the 2 in front of the iron 3 oxide, that makes me have 4 total iron on that side, so I need to put a 4 there. Okay, so here we go. What mass of iron must be used to produce 125 grams of the iron 3 oxide? This is a synthesis reaction, and so we're going to list the 125 grams of our given underneath the product, and then it said what mass of iron must be used. So we're going to be looking for the mass of iron. So this is another mass to mass problem. So pause the video, work it out, and then let's see how your answer compares to mine. Here we go. See how you did. And again, if you didn't get the same thing I did, then pause the video and look at your steps compared to my steps and see where you're making your mistake. So let's do one last problem on the next slide. All right, last one we're going to do on this tutorial, and we're going to end it with the big one, which is a limiting reactant. And the reason that I know that this is a limiting reactant is because it gives me 207.5 grams of zinc reacting with this many grams of hydrochloric acid. So because it gives me 2 reactants, it's going to be limiting. And so it's going to be solving for mass of zinc chloride. So if you recall, we're going to work the problem once using the zinc and once using the hydrochloric acid. So let's balance this equation really quickly. I see that I have 2 chlorine and 2 hydrogen on the product side, and I only have 1 of each on the reactant side. So I'm going to fix that by putting a 2 right there. Okay, so it gave me 207.5 grams of zinc, and it gives me 150.8 grams of hydrochloric acid. And then, of course, I am solving for grams of zinc chloride. So I'm going to work the problem once using zinc and solve for zinc chloride, and then I'm going to work it the second time using the HCl and solve for the zinc chloride. And then whichever gives me my smallest answer is going to be the correct answer, because once we run out of one of the reactants, we can't keep making product. And then whatever gives me that smallest answer becomes my limiting reactant. All right, so pause this video and work it out. And I'm actually going to need you, when you're done, to go to the next slide, because there's not enough room for me on this slide to work the problem. So when you're done, go to the next slide and see what you get and see if you get it correct. All right, how did we do? The zinc should have given you 432.9 grams of zinc chloride, and the HCl should have given you 281.9 grams of zinc chloride. So clearly that's the smallest answer, and so it is our answer to how much product we could produce, because we would run out of HCl before we ran out of zinc. So that makes HCl our limiting reactant, and that makes zinc our excess reactant, meaning we would have that left over, but because we ran out of HCl, we couldn't keep making product. So hopefully this helped you out a little bit. If you're still struggling, you need to come in for some one-on-one tutorials with me. I hope you have a great day. Bye.